Welcome to The Explainer. Today, we are cracking open a massive forensic cold case file on the greatest, most sudden biological revolution in our planet's entire history, the dawn of complex animal life. Okay, let's dive into this. For decades, the Cambrian period, which kicked off roughly 540 million years ago, has been one of science's greatest mysteries. I mean, we went from simple, squishy, soft-bodied organisms to an absolute explosion of bizarre, complex, heavily armored life forms in a geological blink of an eye. But modern science, armed with some incredibly cool new biomechanical and geochemical tech, is flipping our oldest assumptions completely on their head. Here is our roadmap for today's explainer. First, triggering the explosion. Second, the Burgess Shale time capsule. Third, rethinking the apex predator. And finally, the hallucigenia identity crisis. All right, Section 1, triggering the Cambrian explosion, how a geologic anomaly sparked complex life. This sudden burst of biological diversity didn't just happen out of nowhere. It required a massive environmental spark. And research points right to a geological curiosity known as the Great Unconformity. Basically, this is a dramatic worldwide boundary in the rock record, where ancient, billion-year-old igneous and metamorphic basement crust sits right underneath much younger Cambrian marine sedimentary deposits. During the early Cambrian, shallow seas kept advancing and retreating, wearing down the surface and exposing this raw, highly reactive, deep-crust rock to the ocean for the very first time. Which brings us to this really fascinating hypothesis from geoscientist Shannon Peters. When those ancient continental rocks were finally exposed to air and water, they underwent severe chemical weathering. And we're talking about an event that literally flooded the Cambrian oceans with a massive influx of ions, things like calcium, iron, potassium, and silica. It fundamentally changed global seawater chemistry. So the crucial point here is that early animals didn't just casually invent shells and skeletons because it sounded like a good idea at the time. This massive influx of minerals would have actually built up to highly toxic levels inside the bodies of these simple, soft marine creatures. To survive, they had to actively excrete those ions. Developing biomineralized hard parts, shells, spines, skeletons, was basically an evolutionary reaction to a massive environmental crisis. They were quite literally sweating out mineral salts just to stay alive. And in doing so, they kicked off an epic evolutionary arms race. Moving right along to Section 2, the Burgess Shale time capsule, unlocking the taphonomic vault. Honestly, it's a miracle we know anything about these early soft-bodied creatures at all. Normally, an entirely soft organism completely decomposes long before it has any chance to fossilize. Yet, in specific deposits like the famous Burgess Shale, we find these incredible carbonaceous compressions of the animals. The anatomical detail that gets retained down to delicate legs and antennae is just mind-blowing. It represents a highly unique taphonomic window, which is just a fancy way of saying a very specific set of environmental conditions aligned perfectly to conserve soft tissue in the rock record. So how did this taphonomic vault actually lock? Well, research out of Pomona College gives us a precise three-step forensic recipe. First, the creatures were rapidly buried in fine-grained clay deep down in oxygen-depleted waters below the chemocline. Second, those early Cambrian oceans naturally had super low levels of oxygen and sulfate. And since those are the main ingredients bacteria need to decompose organic matter, microbial decay basically ground to a halt. But the absolute clincher is step 3, early carbonate cementation. And this brilliantly illustrates that exact third step in action. Those bright orange bands you see concentrating at the tops of the fossil-bearing beds, those are early carbonate cements. They precipitated straight out of the seawater incredibly quickly after the animals were buried. So they effectively shrink-wrapped the sediments, locked out any remaining oxygen, stopped decomposition dead in its tracks, and perfectly preserved the carbon films of the animals trapped inside. And here is the kicker. This incredible preservation wasn't just some lucky local fluke up in the Canadian Rockies. It was actually a global phenomenon. Why did these carbonate cements form so easily all over the world? Well, it ties perfectly back to what we talked about in segment 1. The Great Unconformity had totally flooded the oceans with calcium, creating highly alkaline seawater. So the exact same chemical anomaly that forced life to grow skeletons also provided the perfect concrete fault to preserve them. How cool is that? All right, let's hit Section 3, rethinking the apex predator. The truth about Anomalocaris canadensis. For a really long time, the 3-foot-long Anomalocaris canadensis was viewed as the absolute monster of the Cambrian. The old view painted it as this heavy, bottom-dwelling brute that prowled the seafloor, using spiky frontal appendages to violently crush the hard shells of trilobites. But recently, a research team ran this creature through modern biomechanical testing, and the new view? It completely upends its fearsome, shell-crushing reputation. When analyzing the spectacularly preserved frontal appendages of this animal, researchers zeroed in on the downward-pointing spines, which are called endates. Using 3D digital modeling and finite element analysis, which is literally the exact same engineering tech we use to test the structural integrity of bridges and car parts, they tested exactly how much force these appendages could actually handle. And the digital stress tests were super definitive. Those long, thin endites experienced very high microstrain and plastic deformation, meaning if Anomalocaris actually tried to strike a hard biomineralized trilobite shell, its arms would simply snap. Plus, across all the fossil specimens we have, there's basically zero evidence of regularly broken or stunted spines. Even its circular mouth plates turned out to be way too pliable to crush shells. True shell crushing, or durophagy, was left to completely different, much heavier predators. So, if Anomalocaris wasn't a bottom-dwelling shell crusher, what on earth was it? Now, what's really interesting about this is how computational fluid dynamics gave us the answer. By testing the drag coefficients of the appendage in various postures, from tightly curled up to fully stretched out, researchers discovered that holding the appendages out straight produced remarkably low drag forces. This means Anomalocaris was hydrodynamically optimized for pure speed. It definitely wasn't a sluggish bottom feeder. It was a highly agile, swimming predator. It darted through the well-lit upper water column, using acute vision and explosive bursts of acceleration to snatch up soft, squishy prey with those delicate front appendages. Finally, Section 4, the hallucigenia identity crisis, flipping the Cambrian right side up. If you ever feel a little lost at work, just remember it took the scientific community 50 whole years to figure out which way was up on hallucigenia. Back in the 1970s, this tiny fossil was reconstructed completely upside down. They thought it walked on the ocean floor on stiff stilts with a row of weird tentacles waving around on its back. By the 90s, scientists realized those tentacles were actually paired legs, so they flipped it over. But it wasn't until the 2020s, using electron microscopes, that researchers finally found its head, complete with simple eyes and a throat ringed with teeth. So what did the real hallucigenia sparsa actually look like? Well, it was tiny, maxing out at just 5 centimeters long. It walked along the seafloor on 7 pairs of clawed legs, while proudly displaying 7 pairs of sharp, defensive spines on its back. Instead of an evolutionary dead end or some impossible weird wonder, we now know it makes perfect biological sense. It's an early lobopodian, making it a true ancestor to modern-day velvet worms and those indestructible microscopic tardigrades. Okay, I have to share my absolute favorite detail about this whole identity crisis. For decades, scientists couldn't locate the head because one end of the fossil always featured this large, unidentifiable blob. Well, it turns out that wasn't a head at all. Remember that intense, rapid burial in deep mud we discussed during the Burgess Shale preservation segment? That burial was so forceful that it literally squeezed hallucigenia's guts right out the back of its body. That mysterious blob was just an ancient, fossilized splat. Let's bring all of these threads together and see how this builds a much clearer picture of the Cambrian. The deep crust is exposed, fundamentally altering the chemistry of the entire ocean. A massive spike in toxic minerals forces soft-bodied organisms to build protective armor. Those highly alkaline waters then provide the perfect, rapid cementing conditions to preserve the victims and the victors of this brand new ecosystem. Meanwhile, apex predators like Anomalocaris adapt to hunt with speed in the open water, while tiny wonders like hallucigenia armor their backs with spines just to survive on the seafloor. It's just a great reminder that our understanding of the past is never static. Paleontology today is a highly active forensic science. By leveraging computational fluid dynamics, geochemical sampling, and finite element analysis, we are turning what used to be a flat, static picture of a rock into a dynamic, living, breathing ecosystem. We are literally breathing life back into these 540-million-year-old cold cases. Thanks for diving into this Cambrian cold case with me today. It really makes you wonder, doesn't it? As our tech keeps evolving and getting more precise, what other established facts about our planet's deep history are just waiting to be flipped completely right side up? Keep questioning, keep learning, and I'll catch you in the next explainer.